Digital Logic, an introduction to Boolean expression minimization. Welcome to this essential session on digital logic. We'll explore powerful techniques to simplify Boolean expressions, which is crucial for efficient and robust digital circuit design. Mastering minimization saves costs, reduces power consumption, and improves circuit speed. Agenda: streamlining digital design. Why minimize? Sum of products, SOP, product of sums, POS. Understand the critical importance of simplifying Boolean expressions in digital circuits. Learn the fundamental form for expressing logical functions. Explore an alternative, equally powerful form for logic representation. Karnaugh maps, K-maps. Practical applications. See how these techniques translate into real-world circuit design benefits. Master a visual, intuitive method for minimization, particularly for 2 to 4 variables. Why minimize Boolean expressions? Efficiency in design. Increased speed. Minimization directly translates to fewer logic gates and interconnections needed for a circuit. This reduces manufacturing costs and complexity. Simpler circuits have fewer propagation delays, allowing for faster operation and higher clock frequencies in digital systems. Reduced power consumption. Improved reliability. Fewer gates mean less active components, leading to lower power dissipation, crucial for battery-powered devices and large-scale integrated circuits. With fewer components, there are fewer points of failure, increasing the overall reliability and lifespan of the circuit. Sum of products, SOP, the building block. SOP is a standard way to represent Boolean functions as a sum, OR, of product, and terms. Each product term, minterm, corresponds to a specific combination of input variables where the output is 1. This form is directly implementable using an OR logic gates. It's often the starting point for minimization techniques like Karnaugh maps. Product of sums, POS, an alternative perspective. POS expresses a Boolean function as a product, and, of sum, OR, terms. Each sum term, max term, corresponds to a specific combination of input variables where the output is 0. This form is directly implementable using OR and logic gates. It provides a complementary approach to SOP, sometimes simplifying the logic more effectively, especially when there are fewer zeros in the truth table. Karnaugh maps, K-maps, visual minimization. K-maps provide a graphical method to simplify Boolean expressions. They are particularly effective for up to 4 variables, allowing us to visually identify and group adjacent ones for SOP, or zeros for POS, to eliminate redundant terms. Key K-map principles. Each cell represents a minterm, or max term. Adjacent cells differ by only one variable, gray code ordering. Groups must be powers of 2, 1, 2, 4, 8, etc. Groups should be as large as possible and cover all ones or zeros at least once. K-map example. 2 variables. Let's minimize f, a, b, equals ob plus ab. K-map construction. Truth table, 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. By grouping the 2 ones, 01 and 11, we eliminate the variable a, resulting in the simplified expression. Key takeaways and next steps. Master minimization. K-maps for visual simplicity. Practice makes perfect. SOP, POS, and K-maps are indispensable tools for efficient digital circuit design, leading to smaller, faster, and more reliable systems. The best way to master these techniques is through hands-on practice with various examples. Try designing simplified circuits based on truth tables. For up to 4 variables, K-maps provide an intuitive way to simplify complex Boolean expressions by identifying adjacent terms. For more complex expressions, 5+ variables, consider Quine-McCluskey method or dedicated software tools. Thank you.